Hey, it's Mr. Ayton. Welcome back to Pre-AP Chemistry. We are in a new unit, Unit 6, Chemical Reactions. We are in Week 10, and let's take a look at what we're going to look at in Week 10, which is Chemical Reactions. We're going to look at chemical changes. Remember, when we were at intermolecular forces in Unit 5, we were looking at physical changes, but now we're taking a look at actual chemical changes. We're going to look at what net-ionic reactions are, precipitation reactions, and oxidation-reduction reactions. So let's get to our chemical reactions. What is a chemical change? Well, if you remember, a physical change is the breaking of attractions, breaking and forming of attractions or intermolecular forces. We didn't change the substance. It went from H2O liquid to H2O gas when we broke those hydrogen bonding attractions. But a chemical change is literally breaking or forming chemical bonds. We make brand new substances. If you can take a look, here we have CH4 methane plus 2 oxygen gases, and it's breaking those bonds. It's forming other bonds, which we call reactants, forming into products, and that is a chemical change. And there is a law of conservation of matter. There's a law of conservation of energy as well, which means our number of atoms have to be conserved. You can see there's 4 red oxygens at the beginning in the reactants. There's 4 red oxygens as products. We don't lose any mass. We don't gain any mass. We conserve mass and we conserve energy. And we in Pre-AP Chemistry are going to be doing what's called net-ionic chemical reactions, which means, what does a net mean? A net means you're going to be very soon going and getting a job, and you're going to get a gross salary. A gross salary is going to be like everything you make over 2 weeks. And then they're going to take off money in taxes and insurance and all that stuff. And at the end of the day, you're going to make a net sum of money. And guess what? This net shows what's actually, what are you actually getting? And in the same way, a net-ionic chemical reaction, it only shows the species that are involved in the chemical reaction. It doesn't show all the stuff behind the scenes, the stuff that's not reacting. It does not show what's called spectator ions. It shows just the net of what happens, okay? Which means we're not going to show spectator ions in our chemical reactions. And so you want to know what spectator ions are not going to be shown. Well, nitrate is a big one that is never going to be shown, nitrate. Always eliminate nitrate. Nitrate's never going to react. Also, alkali metal ions, something like sodium ions, potassium ions, lithium ions, these guys, alkali metal ions, these are never going to react together, okay? Now, if you know these kind of two, you can pretty much get through anything. There's also other spectator ions, but these are the ones that normally are always going to be spectator ions, and you can just kind of cross out, okay? So let's get to our first type of reaction, which is called a precipitation reaction. At most high schools, you would learn about double replacement reactions, but double replacement reactions is not what's actually happening. A double replacement reaction, it has spectator ions. What's actually happening is things are precipitating. We have a cation, a positive cation, and a negative anion, and they're combining to form, of course, an ionic solid called a precipitate, okay? These are going to be electrostatically attracted together to form an ionic solid, a precipitate. So if you have positive ions at the beginning and negative anions at the beginning as well, the conductivity is really high. But as we form a precipitate, an ionic solid, the conductivity gets less and less and less. And spectator ions are not present in a reaction. And what do we get is a solid precipitate here. Okay, so let's take a look at 2 examples. We're going to take a look at the first one, which is aqueous solutions of silver 1 nitrate. So we have silver 1 nitrate. What is silver 1 nitrate? We have silver ions, which are positive. We have nitrate ions, which are negative. Okay, and those are split up. It's dissolved in water. That's what an aqueous solution means. And then we also have an aqueous solution of sodium chloride, sodium ions and chloride ions. Again, these are broken up, which means you can see these ions and these ions are moving around. Very high conductivity as these move around. But when we mix these two together, remember the spectator ions don't do anything. So the nitrate and the sodium ions aren't going to do anything. They're still going to be in the solution They're still going to be dissolved. They haven't really done anything. But the Ag plus and the Cl minus are going to react and electrostatically attract each other and make an ionic solid. And this ionic solid is going to be a nice kind of white solid, and it will be a white solid at the bottom of my container here. And so this is called a precipitation reaction. Now, when we write the precipitation reaction, we want to show what's actually happening. And you think about it. All that's happening is the silver ions, which are aqueous, and the chloride ions, which are aqueous, they are going to produce silver chloride, AgCl solid, an ionic compound. Okay, you can see I didn't put the Na plus and the NO3 minus in my reaction because those ions are not actually doing anything. They're just spectators. And so my precipitation reaction is Ag plus and Cl minus makes AgCl. And you can see we need a 1-to-1 ratio because they cancel out and make it electrically neutral ionic solid. Let's take a look at our second example of a precipitation reaction. Here we have lead 2 nitrate. We have lead, which is Pb plus 2, and we have nitrate. Now think about it. If nitrate's -1 and lead's positive 2, then we're going to need 2 of these nitrate ions here. Okay, and remember, they're dissolved, they're broken up, they're moving around in solution. Then we have potassium iodide. We have K plus and I minus, K plus and I minus. And we might have another K plus and I minus, and you can see these are moving around in solution. Okay, now think about it. What is not going to react? What are going to be spectator ions? Obviously, the nitrate and the potassium ions are not going to react. Only the lead ions, the Pb plus 2, are going to react with the I minus and I minus. And why do we need 2 of those I minuses? Well, we got to cancel out this charge. And that's going to make a solid at the bottom, a solid precipitate. And what's still going to be left in solution is the K plus and the K plus. Those didn't react. And the NO3 minus and the NO3 minus. And those didn't react as well. Okay, and so those are spectator ions. We're not going to show those. And what do you know? This makes a solid, and as we're going to take a look in class, this PbI2 is like a big yellow solid right here. Okay, and so when we go to do our chemical reaction, what's actually reacting? Well, the lead ions, which are aqueous, are reacting with 2 of these iodide ions, not just 1, but 2 of these iodide ions. And why do we put a big 2 right there? Well, we have to balance this reaction. And what does it make? It makes PbI2 solid, PbI2 solid. And you can see, let's look at our atoms. We have 1 Pb at the end. It's conserved. We have 2 I's here, and we have 2 I's here. Those iodines are conserved as well. And if we take a look at our charges, we have positive 2 for the lead. We have 2 minuses, which cancels out and becomes 0, and of course a solid is a 0 charge. So those are good examples of our precipitation reactions. Let's move on to what's called oxidation-reduction reactions. Now in most classes, most high schools, you would do these as single replacement reactions, but remember, double replacement and single replacement, it's not what's actually happening. It's a very elementary way to look at reactions. We want to look at what actually happens. And what actually happens here is an element is going to be oxidized, which means losing electrons, while another element is reduced, which is gaining electrons. So there's an exchange of electrons. And if there's an exchange of electrons, if electrons are being transferred, then electricity is being produced because electrons are moving here, okay? And a great way to remember that is Leo, the lion, goes grrr. Because losing electrons is oxidation, gaining electrons is reduction. Leo the lion goes grrr, okay, for oxidation-reduction reactions. So let's take a look at what's happening in one of these oxidation-reduction reactions, okay? Here we have a piece of solid zinc. So I'm going to draw a piece of solid zinc. So here's a piece of solid zinc. And we have zinc. Remember, zinc's a metal, which means it's going to be metallic intermolecular forces. And you can see a bunch of zinc atoms here, zinc atoms, zinc atoms, zinc atoms, okay? This zinc has all its electrons. And here we have copper 2 nitrate. Copper is positive 2 and nitrate is -1. So I need 2 of those nitrates, okay? So these are in a solution, so they're aqueous, they're broken up, okay? So what's going to happen here is this. Remember, the nitrate is a spectator ion. The nitrate's not going to do anything. This copper, as it comes and bounces and collides with this zinc, okay? As this copper collides with the zinc is going to lose 2 electrons. So the zinc is going to lose 2 electrons. And the copper is going to gain 2 electrons. And think of what happens when the zinc loses 2 electrons, it becomes zinc plus 2, doesn't it? Okay, it becomes a cation. And you can see what happens here is this zinc kind of gets broken up. It's this solid zinc is losing mass, isn't it? It's not really losing mass. The mass is still in this zinc plus 2. But this solid zinc is kind of dissolving, okay? And this copper gained 2 electrons. So when positive 2 gains 2 negatives, it becomes copper with a 0 charge, which is a solid. And what kind of color would that be? Well, you know what copper is. Copper is kind of that brown color, and you can see it's a solid. It's at the bottom there. So we start kind of precipitating this copper. The zinc kind of gets dissolved, okay? So let's take a look at what a reaction would look like. We have zinc solid, okay? And remember, the nitrate's not reacting, so the nitrate's not really doing anything. We have copper is going to be plus 2. Copper is going to be plus 2 because that's aqueous, isn't it? That's aqueous. And what happened on the other side? The zinc went from a 0 charge, it lost 2 electrons, and the zinc becomes positive 2, and the zinc is now aqueous. It's dissolved. And the copper gains those 2 electrons, and the copper becomes a solid 0 charge, doesn't it? And you can see what happens here is the zinc lost 2 electrons, the copper gained 2 electrons. Okay, and so we see this kind of happen here. Well, in this reaction, we actually see what happens. The zinc gets dissolved, doesn't it? The zinc goes from a solid to an aqueous. It gets dissolved. The copper goes from an aqueous to a solid, so we see the copper precipitating out. Also, this blue solution of copper, which is a blue solution, starts to become a little bit more clear. So that's a good example of an oxidation-reduction reaction. Let's take a look at one more oxidation-reduction reaction. Here we have solid magnesium, so I'm going to draw a piece of magnesium solid. It's a metal, it's an alkaline earth metal, so magnesium solid, all these atoms here. And it's in hydrochloric acid, so I have HCl, and you can see this is aqueous, so this is all broken up. It's conducting electricity here. And what happens here is this. Again, one of these magnesium, when the H plus hits this magnesium, the magnesium is going to lose 2 electrons. Why will it lose 2 electrons? Remember, magnesium has 2 valence electrons. And so it loses an electron here and loses an electron here, which means the magnesium, this magnesium becomes magnesium plus 2, doesn't it? It gets dissolved. And what happens to this piece of magnesium solid? It starts to dissolve, doesn't it? It starts to dissolve, okay? And what happens with this H plus? When this gains an electron and this gains an electron, these 2 H pluses, they bond together. They bond together to make hydrogen gas. And that hydrogen gas goes out, doesn't it? So we're going to see some bubbling going on here, and this hydrogen gas goes out of the solution here. Okay, so what we get left with is a bunch of magnesium. Now you can see the chlorides didn't do anything. Those are spectator ions. So we're not going to put those in our reaction. So let's do a balanced reaction. We have solid magnesium. Solid magnesium, remember, has a 0 charge. And it's reacting, remember, it reacted with 2 of those H pluses, didn't it? 2 of those H pluses. And what did the magnesium become on the other side? It became magnesium plus 2. Again, why did it become positive 2? Is magnesium has 2 valence electrons. It's an alkaline earth metals. And what did the H become? It became H2 gas, a covalent molecule there. And you can see what happened here is the magnesium lost 2 electrons. It was being oxidized. The H plus gained 2 electrons. It was becoming reduced. And what do we see? What do we observe happening is the magnesium is getting dissolved. we're producing a gas. We see bubbles going on here, and that's a nice example of an oxidation-reduction reaction here, an oxidation-reduction reaction. And so, yeah, that should say oxidation-reduction reaction. That's a little copy and paste error. So, sorry guys. This is week 10, unit 6, chemical reactions. A little bit complex, but I think we'll be able to work through this in class, and make sure you take a look at your self-assessment, and I'll see you on the flip side, pre-AP chemistry. See you guys. Bye.